Hello, my name is Veronica Padakova. It's January 25th of 2026, and we are looking at combined spectra problems. We are given a compound with the molecular formula of C9H12, and we're looking to propose a structure for it. First, we'll calculate the degree of unsaturation or sites of unsaturation, and by applying a formula, we can see that we have number 4, so that's our degree of unsaturation. It indicates that we do have double bonds present in our compound, and in particular, it does indicate that we do have aromatic rings. The infrared spectroscopy help us to identify present functional groups in the compound. For example, we could see at 3100 to 3000 the presence of the aromatic stretch carbon hydrogen. We can also see carbon-carbon stretches that are indicative of aromatic compounds or aromatic rings. And we also see a 735 carbon hydrogen out of plane bending that represents the aromatic ring that is mono-substituted. So these 3 peaks can help us to build a proposed structure, but we do want to analyze other spectra in order to look at carbon and hydrogen environment. Carbon NMR can show us the carbon environment in the compound. Now we could see the aromatic ring. Now it's important to know that the same range is observed for non-aromatic alkenes. It's about 110 to 150, but because we did have an infrared spectroscopy indicating the presence of aromatic ring, that gives me confidence that this is our aromatic carbons. Now the shift, the downfield shift, can be explained by the anisotropy of the induced field generated by the aromatic ring current. And we can also see that we have 3 carbons also separate from the aromatic compound, that it indicates the alkyl chain. I do see that 1 carbon is shifted a little more downfield as compared to other. It is more de-shielded by the presence of an aromatic ring. So and then we have the terminal carbon because it is not as de-shielded as this carbon, for example. It's in a different environment. Now, 1H NMR can show us environments for hydrogens or protons in the compound. We can right away see the largest peak with 5 hydrogens. Now, at 7.02 to 7.4, that is indicative of a benzene ring, and because it's mono-substituted, it makes sense that there are 5 hydrogens. It appears as a one big peak. Now, when looking at the hydrogen environment, it's also important to know the anisotropy of the field generated by the aromatic ring. Protons are highly de-shielded. That's why we can see this shift of protons in the benzene ring. Now we do follow the general rule of n+1 when looking at the hydrogen NMR, meaning that, for example, we have a peak at 2.6 and it appears as triplet, and that tells me that the neighboring carbon has 2 hydrogen plus 1 gives us triplet. So that tells me that and I don't see anything else, and because of the shift to, I think that is the hydrogen on a carbon that is attached to benzene ring. And then we have a sextet which is normally seen by because the integration is 2, it's the CH2, and it's bonded to terminal carbon and then the other CH2 carbon, and it gives us 5 hydrogens plus 1, 6 sextet matches, and then we have a triplet final, and it's an integration of 3, and it's right here. So it's not as de-shielded as compared to these 2 hydrogens, for example, of these 5 hydrogens. So it tells me that it's a terminal hydrogen attached to CH2 group. So that does confirm the benzene structure, and then we have a propyl chain. So to conclude, we were able to determine that we have a benzene ring. We have a benzene ring that is monosubstituted. We saw that the carbon shifts are indicative and support the benzene aromatic shift. And we did see a 3-carbon chain also in carbon MNR. And the hydrogen MNR and the proton environments did tell us a little more about the connectivity. So we were able to identify that our compound is propylbenzene, and it's a benzene ring, and we have a propyl chain attached to it, a propyl group attached to it. And thank you.